No planned fire alarm this afternoon, so if the fire alarm does go off or there is an emergency, we have to evacuate this space by the staircase by which you entered towards the back. If you have any if you have any mobility problems, please will you let one of the members of staff know, who are usually the gentlemen and ladies with the red t-shirts saying Royal Society. So this discussion is entitled Blunders and Breakthroughs, and is to examine how ideas may have been before their time in history, scientific ideas. Perhaps we can look back on them now and think, well, how could people have been so wrong, been so misguided? What was the view at the time? Did following so-called wrong theories, wrong ideas, lead to scientific breakthroughs in due course? And we have a panel of experts here to discuss a variety of different scenarios. I'm Tilly Tansey, and I'm a neuroscientist who became a historian of medicine. On the far right, we have Professor Jerry Gilmore, who is originally from New Zealand, and he's now at the University of Cambridge, where he's Professor of Experimental Philosophy. He's an astronomer who studies the nature, in particular, and origin of our galaxy, the Milky Way. And he, in particular, has pioneered the study of spectral surveys to determine the galaxy's history using chemical techniques. In the middle is Helen Chatterjee, who is a professor of biology at University College London, UCL. Her biological research is focused particularly on primate phylogenetics and morphological adaptation, and she's especially interested in gibbons. And if you look on her website, she is actually known privately as a professor of gibbonology. She also has another job at UCL, that she is the head of research and teaching for what is called UCL Culture, and that includes responsibility for all UCL's museums, collections, theatre, studio, and public engagement. And on my immediate left is Professor John Worrell, who is Professor of Philosophy of Science at London School of Economics. He has principally worked in the history and philosophy of physics, but more recently he's moved into medicine, and in particular the areas of evidence and policy and evidence-based medicine. So we have a range of expertise here today. And what I'm going to ask people to do first of all is to actually talk a little bit to this brief of blunders and breakthroughs, give us an example or more examples from their fields, from their own particular fields of expertise, and how they might interpret this topic. We then will open up the discussion to the rest of the audience to ask questions or make comments, and we'll just take it from there as a general discussion. So, Jerry, could I ask you to perhaps start and think about how you would interpret this blunders and breakthroughs?
Good afternoon, everybody. It's a pleasure to be here with you all. I'd like to raise a general point, is that first it's worth remembering the motto of the society that we are in, nullius in verba, which basically means don't take anybody else's word for it, and is really the way we should all respond to both blunders and breakthroughs, is that make sure you understand for yourself what's going on and not just read something as if it's the Bible. And as one example of how even the great names should not be taken as gospel, we might as well start with the greatest of the locals, Sir Isaac Newton. And in my subject, Newton did a great deal, of course, and much of it was in fact breakthrough. But he, among other things, wanted to understand the distribution of stars in the sky. So he built a model of what the universe should look like, which was going to be published in the second edition of the Principia. And Newton, being rather confident in what he believed, wrote out the complete top copy, in Latin of course, of the book, the second edition, just leaving spaces to come in where he would put in the diagrams and the tables of numbers showing that he was right or how he did something. And so all this was written out. And when he came to fill in the table of numbers of how his model agreed with the numbers of stars in the sky, he had the data. The data were ancient, actually. They were due to Ptolemy, ancient Greek, catalogue of the relative numbers of stars as a function of brightness. And the ancient Greeks developed the system of magnitude. So the brightest stars were of the first magnitude, the second brightest were of the second magnitude, and so on. This is terminology we still use today. and each magnitude layer was supposed to be twice as faint as the others. So Newton, first of all, then went and looked at the data, and it didn't match his model at all. And Newton, being a Cambridge professor, an arrogant philosopher, said, well, I'm smarter than the people who count stars, so they must have done something wrong. So I'll ignore half the data. I'll ignore all the faint stars, because they're probably wrong. That still didn't help. And so he said, well, I'm smarter than these people, and I'm better at everything than these people, so I bet their eyes aren't very good either. So I bet when they count magnitudes of stars, they don't actually find stars that are twice as faint as other stars. And in fact, he deduced that the magnitude scale must be a logarithmic scale, and that our eye-brain combination must be a logarithmic scale, so that a fifth magnitude star is not 2 to the fourth, not 8 times fainter than a first magnitude star, but it's 100 times fainter. And that was correct. So just in an attempt to try and make his model fit the data, Newton made this fundamental breakthrough in why it is that basically we have night vision and day vision and our eyes have such a dynamic range. So that was pretty smart, but it still didn't help his model explain the data. And so he then did the only other thing that he could do, and he did often, which was cheat and adjust some of the numbers a bit. He still couldn't cheat enough to make it work. And so fundamentally, even clever people think. Newton just knew in his heart that nature must be mathematically simple and clean and excellent, and God must have been a mathematician. And therefore, anything that God made must be mathematically elegant. And Newton was extremely religious, totally religious, couldn't imagine anything beyond his own religion. And therefore, he could not imagine a universe that was not mathematically perfect, like a crystal. So he worked out some very elegant spacing theorems to explain where the stars should be, and they weren't like that. And so he just simply didn't know what to do. He had no conception of how to make progress. In fact, he gave up science and went and became a banker. He went down to run the mint, which a lot of people do in their careers. But that's a nice example of a blunder that actually terminated a great man's scientific career, but illustrates to us that most of our limitations are not limitations of what we know, but how we go thinking about it and the mindset which we bring to studying a problem. And from that, we can all learn.
That's tremendous. Thank you very much, Jerry, for bringing in the founder, almost Newton, of the Society. If you haven't seen it already upstairs, there is a facsimile of Newton's telescope. There's actually Newton's own telescope, but a facsimile in virtual reality that you can go and have a look at upstairs before you leave. That's a very interesting example from astronomy, from physics. Helen, what about biology?
So a lot of what I do is about looking at the impacts of environmental change on organisms, and we're really driven by data and method. So picking up on Jerry's points of it's really about that information that you're gathering and how you're using that and how you're interpreting it. So that has a massive impact for us. So I spend a lot of time making evolutionary trees, looking at patterns of relatedness amongst organisms, particularly amongst primates. Tilly's already mentioned the gibbons. Does everybody know what a gibbon is? Most people are nodding. Anybody not know what a gibbon is? Come and see me afterwards. So I spent 20 years working on gibbons. Small apes from Southeast Asia, and we've had lots of blunders trying to work out how different species of gibbons are related to each other, and indeed how many species of gibbons there are. So when I first started working on gibbons, there were 6 recognised species of gibbon. Now there are 20. There's been a new one named in the last few months. And that just gives you an idea of what we thought we knew at the time 20 years ago, and our understanding of what an organism is and what a species is can be radically affected by new information. And at the time we had no prediction that there was going to be so many species recognised. And that's not new animals that have been discovered, that's a better understanding of those organisms that we already knew, both in the wild but also things like their DNA. So big advances in amplification of DNA enabling us to look at looking at relatedness from the perspective of how genes are related. So we're always seeking that true tree of evolutionary relatedness, that true gene tree, but whether we can find that or not is a big question for us, and it really hinges on the type of data that you put in. I work on both morphological data, so looking at hard tissue, bones, fossils, as well as soft tissue data, and also genetic data, and using those different lines of evidence can give very different interpretations of relatedness. And also abiotic factors, so things like the environment and the implications that that has for those sorts of data predictions. So that's having a big impact for my work now, particularly thinking about how organisms are changing in the present day. I'll spend a lot of time looking at the past and how we can make predictions looking at the past and the present in terms of the future, so thinking about climate change and what impact that's having on organisms. In relation to the impact that humans are having on environmental change. So trying to bring all of those different types of abiotic data into making predictions is also quite challenging and can really affect what we might predict for the future.
A lot of food for thought there, Helen. John, what's your take on this remit?
Yeah, thank you. Well, like Jerry and Helen, I'm very pleased to be here. Thank you for coming. I'm a bit of an anti-romantic. We were asked to think about, particularly about blunders, things that look like blunders at the time. Of course, Jerry's right that even the greatest scientists make mistakes. It looks like Einstein's idea of a unified field theory is not going to work, for example, and they don't come any greater than Einstein. But what we were encouraged by the organisers to think about were things that were claims that were regarded as blunders, or steps in science that were regarded as blunders at the time, but which turned out to be later in the later science great breakthroughs. And it's surprising that I can't think of any. I mean, I don't think I have completely encyclopedic. May well be some, but it's remarkable. They're remarkable for their absence, I think. I mean, what happens, of course, in science is that scientists make mistakes, but mistakes are a lot different from blunders. And of course, we learn from mistakes. Taught us this. We didn't need Karl Popper to tell us, really. Obviously, we try out things, and sometimes they work, sometimes they don't. So, to give an example again from Newton, from Newton's theory, Herschel discovered a new planet in the 18th century by patient observation. Planets don't come labeled planets, obviously. We only see them as planets because they're moving very slowly against the background of the fixed stars, and we have to be lucky and patient to observe them. And it was called Uranus, and when Newtonian theory were applied to Uranus, it turned out that the theory got it wrong. But of course, you don't deduce consequences just from the basic theory. You've got to make auxiliary assumptions about the initial conditions. And in particular, you've got to assume how many other planets there are. And of course, you took at the time the planets that were known, and that led to a value for the total force acting on Uranus, and that gave a prediction of how it would move, and it doesn't move like that. So in England and Leverrier in France, or if you're a French historian, only Leverrier in France, said, look, Newton's theory's got to be true. Some people said Newton's theory is false. It's not 1 over r squared in the expression for the universal principle of gravity. It's 1 over r to the 2.001, and they fiddled around. Other people said, no, Newton's theory's got to be true. So let's work back. And what auxiliary assumptions would we have to make to get the correct prediction about Uranus? And in particular, maybe there's another planet such that if we feed that into its effect on Uranus into the total force acting on it from all the other planets plus the sun, we'll get the right prediction. And they worked backwards, and they predicted the existence of a new planet called Neptune. That was a great success. But then there are other anomalies around it. No theory ever gets everything right, no matter how wonderful it is. So there were other planetary anomalies. In particular, it was known that Mercury didn't move the way that it should according to Newton's theory. The way that its perihelion, the point at which it comes closest to the sun, precesses over time, was inconsistent with the Newtonian prediction. So Leverrier thought, all right, I'll do the same again, and finished up doing exactly that thing. Newton's theory must be true. let's work back and see what we have to assume about another planet, this time a planet even closer to the eventually, this mistake wasn't solved within the Newtonian paradigm, as Kuhn would say. It turns out to be one of the great successes of Einstein's theory that it explains the precession of Mercury's perihelion. So mistakes are great. It would be nice and romantic if there were really great blunders that were regarded as blunders at the time, that we now think of as potential breakthroughs that weren't developed. I would love it if somebody in the audience could tell me some, because I don't know any. Thank you.
Thank you very much, John. You make an important distinction, I think, between a mistake and a blunder. Blunder, I looked it up in the Oxford English Dictionary, and a blunder is classified as an error due to stupidity or carelessness. And I think what we've been talking about is really more just an error, just not a major blunder, and changes how our perceptions and perspectives change. And two of you have already mentioned slightly and then quite deliberately, Helen, changes in technology, where technology will allow you to develop an idea that seemed to be static or not going anywhere, that suddenly you can then develop it because of an advance, a change in technology. Would you like to say something more about that, particularly in your field of how you reevaluate some of this data you were talking about?
Yeah, I guess the big thing for us is the advent of PCR, so polymerase chain reaction, and the amplification of DNA, and what that opened up for looking at, for example, relatedness of organisms, what it means to be a species, looking at the genome and what aspects of the genome code for different bits of stuff. So if you're interested in evolution like I am, you're looking for those parts of the genome that may have evolutionary informative aspects, so that you can use those to make a prediction about how those organisms are related. And that really massively changed our understanding, particularly in groups that I work on in mammals, our understanding of how those organisms were related. So, you know, some of the headlines that hit, particularly in the kind of late 80s and 90s, pictures on the front cover of the news, all the newspapers, Nature as well, of cows and dolphins jumping out of the water. Does anybody remember that? And how radical that was for the scientific community as well as the wider public. Because up until then, the idea that a cow and a dolphin might be closely related it seemed quite absurd. And it was only an enhanced understanding both of their genetic relatedness, but also actually some of the fossil people who'd for a while been saying that some of the very early bovids, some of the early artiodactyls had some of these ancestral traits that looked like they had water, marine, aquatic adaptations. Suddenly those two lines of evidence could be brought together and didn't seem so crazy. And now everybody considers, or certainly in the scientific community, considers that artiodactyls and cetaceans are more closely related to each other than they are to other groups of animals.
So this one technique, PCR, polymerase chain reaction, this is what when you read in the newspapers about people doing DNA analysis, looking at fossil specimens, old tissues that you're referring to, this is what they're using, this is what's enabled a re-evaluation, is it?
So most people now, when they're making evolutionary trees, are always making those trees. If you ever see a pattern of relatedness of organisms, they're using those sorts of data often. But it is often in conflict with what we know from what's called phenotypes, or what you look like, the kind of data that I used to or soft tissue, fossil evidence. That might give you really, really different lines of evidence for how organisms are related. So sometimes those two lines of evidence and those two groups of scientists can come into conflict and disagree.
And Jerry, what about in your field? Is a similar example you could point to, like Helen's PCR, that revolutionised way of looking at past theories?
Yeah, our field is always revolutionised by technology. One of the peculiar things about astrophysics, it's the oldest of the sciences, but under a modern definition of science, it's not a science. Because to be a science, you've got to be able to repeat the experiment. Somebody else has got to do something. inductive and deductive. And that means we're always totally limited by our technology. And the technology for most of the history of mankind has just been the human eye. And it's quite impressive how one can fool oneself. One of the nicer examples which I really like is the mapping of the canals on Mars. Now, this is something that worked right up to the 1930s. People were still drawing maps of the canals on Mars. And again, this tells us more about what people wanted to see than what they did see. At the time, it was a great life in the universe, life on other planets in the universe. And people deduced, starting in about the mid-1850s, that civilization on Mars would probably be as advanced as any civilization on Earth. And the highest peak of technology on Earth at the time was building the Panama Canal and the Suez Canal. So if that was the best we could do on Earth, then those Martians would have been up there building canals too. And so they went looking for Mars canals and found them, because they wanted to find them. Turns out if you strain your eye really hard, everything goes slightly stretched and you get to see basically whatever you like, so you see patterns. There's a nice example, but it was one of technology. As soon as people looked with slightly better telescopes, they realised that Mars is full of round circles. You've probably seen the pictures. All the shapes are round, they're not straight. But people persuaded themselves you could do that. Because it doesn't come down to the Earth. Interestingly, we're now using those same technologies to look for life around all the hundreds of thousands of other planets that we know are out there, but we're still making the same assumptions. People are still spending vast amounts of money, mostly private billionaire type donation money, but vast amounts of money listening for radio signals. Now, radio signals from planets, people on other civilizations, TV, whatever. Radio signals don't come from life. Radio signals come from electrical engineers. And so what is happening here is that people who are electrical engineers are looking for other electrical engineers. And this is a completely different thing than mankind looking for life. And there's a nice illustration of how when we lose the car keys, we look under the streetlight. We won't look by the car because we can't see it. But that is the way our subject develops, and it still does. And later in the discussion, we can come to the fact that we can't even find 95% of the universe. So we're obviously not very good at what we do.
John, do you want to?
Well, we don't have technology in philosophy, so I can't really add to this, but I would like to add a little bit to what I said initially. It's the sort of the other side of the coin, because again, it's something that we were asked to discuss. Not so much, or not at all, cases where people made what were termed at the time blunders, but which then turned out to be would have been big breakthroughs if only people at the time been clever enough to spot it. But the other side of that coin, aren't there many cases where theories that we now regard as false scored remarkable predictive success, because predictive success is the hallmark of scientific status for a theory. And of course there are many. I mean, Newton's theory had many predictive successes. Precession of the equinox is a prediction of the existence of Neptune, as I mentioned before, but we don't think it's true anymore, not fundamentally. I mean, Einstein's theory tells us that it's wrong in every single prediction by a factor of the square root of 1 minus v squared over c squared, where v is the velocity of the body you're looking at and c is the velocity of light, just that's very close to 1 for ordinary motions. And of course it's an assumption that any two events are simultaneous, absolutely, or they're not simultaneous, is completely wrong according to Einstein's theory. But we still nonetheless think Newton's theory wasn't a mistake. So it certainly wasn't a blunder. It wasn't even a mistake, except that it was strictly false, because it was sort of close to the truth. And there are lots of other cases where that's also true. And I was wrapping brains for this to think of cases where theories that we now regard as totally false nonetheless had predictive successes. And this time I was a little less unromantic, because I did come up with one. And that's Laplace's devotion to the theory that heat, I beg your pardon, is a fluid, an intangible fluid called caloric. And it turns out, if you look, Laplace made a famous calculation of the velocity of sound in various media, in particular in air and other media, that corrected Newton's assumption. Newton had assumed that the whole process was isothermal. Laplace postulated that it was adiabatic, and in order to underwrite that assumption, he needed the idea that when there's compression, when the air molecules are compressed, as a consequence of the passage of sound, caloric is squeezed out. And it turned out that his calculation was correct, much better than Newton's. And not only was it correct, but it got correcter, so to speak, as technology went along. The better techniques we had for measuring the speed of sound, the better Laplace's prediction turned out to be. And it essentially required the caloric theory, which of course we now regard as completely wrong, in a sense that we don't think of Newton's theory as completely wrong. Newton's theory is wrong, but not completely wrong. Caloric theory is completely wrong, and yet it still had this empirical success. And there, I think you just got to say, well, logic tells us that every false theory has infinitely many true consequences, and sometimes you get lucky. I mean, the very false claim that I'm 6'7" tall entails the true claim that I'm either 5'7" when I stand up very straight, or 6'7", right? If what's true, and that's a true consequence of a false theory. And so sometimes it'd be amazing if in the whole history of science we hadn't had very false theories that happen to have a true consequence at the empirical level. But they, as you would also expect from probabilistic considerations, they're very rare. Usually, nearly all the great predictive successes in the history of science have been from theories that, although we no longer regard them as historical, as definitely as totally true, but nonetheless significantly, approximately true. Though philosophers had terrible time saying what approximate truth means, but that's the intuition anyway.
Thank you, John. I think we've got plenty of time for questions and comments from the audience, and we do have 2 roving microphones, so if someone wants to ask a question, will you just raise your hand and the microphone will come to you.
So I was wondering, when you consider something like Lamarckism, where the idea that progeny would inherit characteristics that the parent has acquired in its lifetime, and it was sort of widely disregarded after people made the point that if you chop a parent's arm off, then the progeny won't be born without an arm. But with the advent of epigenetics, does that now represent a blunder which later became a breakthrough?
Thank you. So the question was about Lamarckism, and with the advent of epigenetics, does that represent a blunder which now would be regarded as a breakthrough? And Helen, I think that falls very firmly in your area.
I don't know if it's necessarily a blunder. It's more that, I guess, at the time, a few people, not that many, believed in the idea of transmutation, and the idea of Lamarckism came from that idea of things change and you can see them changing, and how does that change happen? There wasn't an understanding of inherited traits, and that those traits had been selected for. And then I guess once, theories of evolution began very slowly to be accepted by some people through natural selection, then that, opens up an opportunity for people to be more open to the idea of epigenetics and the role of
where it was really deemed that characteristics, acquired characteristics, could be inherited and indeed could be manipulated for society's benefit. We had another question.
Can I say something?
Oh, sorry, yes.
Because I'd love it if you'd give me a counterexample to what I said at the beginning, but I've thought about this. I mean, it's easy after the event. There are lots of cases where outmoded theories that didn't do very well at all sort of have resonances with later ideas. I think, so for example, Newton had this corpuscular theory of light that didn't do anything really in terms of predictive success, but in a sense, quantum theory tells us that it's both a particle and a wave. But there's no sense in which Newton's theory led to that development. And I think, again, the epigenetics came out of a distinctively Darwinian framework, developed independently, and then people turned around and said, oh, look, this is a bit like, only a bit, but a bit like Lamarck. It's not that, if only we'd stuck with Lamarck and somehow tried to synthesize it with Darwin, we would have been at epigenetics a lot sooner. So I don't think it's one of those cases. Thank you.
We have a question over here.
Hello. You talked about how technology has improved and allowed us to capture more empirical data. I wondered how improvements in computation has affected each of your respective fields. So for example, we would have been doing statistical tests on pen and paper in the 1930s, and now analysis of DNA analysis, etc. So how have things changed throughout your careers, and what new questions are you asking yourselves now and able to answer because of improvements in computation and data?
So the impact of technology, particularly computational technology. Jerry, would you like to lead on this one, please?
I have spent my entire career being limited by computer power. So we can now do quantitative measurements on very low signal to noise, very low contrast imaging. So for example, the image we have of the Big Bang, the microwave background, which is the energy released in the Big Bang as it was frozen back 300,000 years after the bang. It's a very low contrast, noisy screen across the whole sky, and yet we can do precision cosmology and tell us how old the universe is to an accuracy of 1% and what it weighs and what it's made of. That's entirely because of sophisticated multi-sampling computer techniques, which were not possible 10 years ago. In fact, there's another directly relevant example of that. I lead another satellite program called Gaia that's mapping the Milky Way. And when I made the case for Gaia, which is just approaching its 1 trillionth measurement, it'll come to its trillionth measurement in a couple of months. I was asked in the year 2000, I would ask, what would I do if I had the Gaia data now? And I said I would put it in a warehouse and wait for 15 years till Moore's law catches up, because we're continually on the absolute state of the limit of what we can do, and that's a definition of progress. If you're always pushing the boundaries and pushing the limits. You know, so many people think that, particularly people like me who do cosmology and early universe and whatnot, they think you sort of sit there daydreaming and suddenly have an idea. But it's not true. You're working through mathematics and you're working through calculations, and you know, I spend my time programming computers, and that's what, not looking through telescopes. That's the way it works. And so yeah, we are totally limited, and I'm looking forward to a spectacular advance over the next half a century maybe, when artificial intelligence proves better than we are at doing science. The guy's got the microphone.
Helen, do you want to respond to the idea about computation?
Yeah, again, a massive shift, really. So I would spend hours in the lab desperately trying to get 200 base pairs, a little tiny bit of the genome of a gibbon, out of a hair sample. And if you were lucky, you might do that for 10 samples. Now, obviously, with the advent of really high throughput sequencing machines, that you can extract and amplify DNA in a fraction of the time and amplify hundreds of thousands of base pairs, which is a good thing and also a bad thing in some cases, because not all of that data is informative. But the lucky thing is that the algorithms, you can have much more complicated algorithms, so you can build in better predictive power, which can analyze those data much faster. So you don't have to put all of your sequences into an algorithm and wait 3 days. Which some people do, depending on how much data you're putting in. But it's just the speed and the amount of data, I guess, is the main thing, which is brilliant and also a challenge.
John, do you have a comment on computers?
We
had another question, I think, here at the front.
As so many things in science at the moment will probably eventually be disproved, can the panel tell me whether that increases their belief or decreases their belief in God?
Who would like to take that on first?
I think a philosopher. We need a philosopher.
I think the philosopher goes first.
I don't believe that my disbelief in God could be increased in any serious sense. I think that's there's an issue as to whether you're complete, what some say scientistic. That is, you apply evidence to every field, including claims about the supernatural and so on, in which case I think you have to dismiss it. But I'm not sure about this, since most of what we'll think will be disproved. I think that comes back to my distinction between mistakes, not quite mistakes and outright mistakes. So, you know, there's a sense in which Newton's theory has been disproved, but it lives on in a very important way. NASA, when they're doing their calculations of rocket trajectories, use Newtonian mathematics. They really use Einsteinian mathematics, but Einstein tells them that within the observational error that they're worried about, it makes no difference, and it's easier to do Newtonian maths than Einsteinian maths. And I think that, you know, what quantum mechanics, general theory of relativity, other things that are solid science will live on in some approximate sense, just in the same way that Einstein's theory, special theory of relativity, yields Newton as the V over C goes to 0, just as you get back classical physics in a limiting process out of quantum mechanics. Whatever we learn later will, in these fields, I'm not saying that we won't learn all sorts of other things that we don't know about already, but in these fields we'll just have a similar relationship to those sort of superseded but still living on theories. So I don't think there's going to be as much disproving as you might think.
Helen, Jerry, do you want to comment on your
Well, to comment, this is an very interesting and important question. But I think the fundamental approach is that as science, in the strict sense of the word, has developed over the centuries and has led to technology and so on and has proven enormously successful, we've realised that the boundaries between what used to be theology mixed up with science and science are actually orthogonal. So they're separate things. Whereas previously one was supposed to be an Aristotelian and believe the various religious texts story of where the universe came from, we now know that that's not the way nature did it. But we also realise even better that the ethical underpinning of human life is not something that science currently addresses. And so there is this realm of ethics and human behaviour and the way we mistreat each other, in which people need to develop value systems and systems for operating. Science has nothing to say about that, and vice versa. And it's the and vice versa which is new.
I'm an ethical unbeliever. Ethics and belief in the supernatural, I think. Well, I just think, I mean, this is, Stephen Jay Gould had this non-overlapping magisteria thing. I think it's, I mean, of course, it's true that, you know, Hume pointed out the obvious logical fact that is and ought are two distinct categories. The fact that somebody commits murder doesn't mean that they ought to have done so. The realm of ought is separate from the realm of is. I think that's plain, but I don't think that should be any consolation to the believer, because I think just having ethical beliefs is independent of any belief about the so-called supernatural.
I think we had another question at the front. Question just by you, James. Behind you.
Hi, thank you very much. Just two examples that come to mind. I should start by saying that I do not have a scientific background, but I think what comes to mind is the origin of the imaginary numbers in mathematics, I believe, were indirectly or directly linked to solving an equation about cars and the way you can transform a vertical piston into a circular motion. And that is what I would relate to blunders, as in, you're not looking specifically for that, but it turns out that it's very helpful to another field of science. And my question is, as science evolves and specializes, do you believe that people will have too much specialized knowledge and therefore will not have the ability to find that stuff about other fields, or will be able to communicate with other fields to encourage cross-fertilization of ideas, if that makes sense?
Yeah, so this is almost what you were implying, Helen, with just the overwhelming amount of data. So
yeah, I mean, I think it is a good point, that the point of because you are overwhelmed with data and information, but actually there is a drive across science to become more interdisciplinary. I guess is your point that you're picking up on, is that if you become very focused and your lens is very focused, then maybe you are missing the big picture. And that was a big problem actually with early, for example, evolutionary trees made just on the basis of by people who only understood genes and they didn't know anything about the organisms. They might be ruling out evidence that was clearly related to how those organisms were adapted to their environments and how they were related to each other. And I think, you know, it's got to be a good thing that there is a drive now across all disciplines of academia to become more interdisciplinary. And I actually don't really consider myself to be a pure scientist. I am an interdisciplinarian because I have various other research interests. And I think when you start drawing data and methods and ideas from other disciplines, you can learn a lot more. And I think it's really positive in the UK that there is a big drive towards, whether it's called transdisciplinarity, cross-disciplinarity, or both inter and multidiscipline. So many research councils now, for example, when you apply for a grant, you actually have to state how you are going to be both multi and interdisciplinary, which I think is a good thing.
John, you're
well,
nodding your head.
Not so much. Well, the massive interdisciplinarity is another issue, but certainly maths and physics, obviously. I mean, nobody could deny it. And that it is interesting that maths has often thrown up, from completely independent, for non-physics dependent reasons, theories that then were essential to scientific breakthrough. So the obvious case is non-Euclidean geometry, Riemannian geometry. Without that, Einstein's theory of relativity gets nowhere. And the example that you, and it's long before, Riemann's long before Einstein. And the case you give, I mean, in mathematics, it was just a question of, wouldn't it be nice if every quadratic equation had two not necessarily distinct solutions? But what about x squared plus 1 equals 0? Well, it doesn't have solutions in the real numbers. So let's invent imaginary numbers. That's how that was completely, and this is just let's invent. And then, of course, complex analysis is incredibly powerful in quantum theory and other fields. And that all turns out later. There I think there is this sort of sleepwalking thing that it isn't so clear within science itself, where for no good physics reasons, mathematicians have happened to develop theories that were then crucial for physics.
The famous physicists and mathematicians who have made the statement that mathematics is unreasonably effective. And it is, for reasons that we do not understand at all. A mathematical logical system that we believe we invented just using basically Greek assumptions about logic turns out to be a superb description of the most extreme forms of existence that the universe is able to maintain, and probably of other universes as well. And that's kind of interesting, and it does mean that all mathematics is probably applied mathematics eventually when you get to it, even though most people don't think that at the time they invent it. You've just heard one example, there are many. But it is also underpins a rather more interesting, potentially interesting assumptions. Because we don't know why it works, we don't know that it will always work. And so this leads us to the concept of, well, is there a limit to our understanding? Is the universe potentially, or something in the universe, so complex it is literally beyond human understanding? And that is what I meant earlier when I said about artificial intelligence. It's very easy to imagine something much smarter than me, and so we'll build it and we'll call it a robot. And so maybe this is the progress. It's also true, your other point, they were very perceptive points you made, that there is now so much information, subjects have been developed to such a high extent, it is no longer possible for any individual to be adept at several subjects. Never again will the concept of Renaissance man or Renaissance woman apply. It just can't be done. And our response to that is fundamentally meetings like this. We understand through the Royal Society and what we do that what we do is very complex. It's taken me 50 years to learn enough to know what I do. I can't expect anyone else to learn it in 50 minutes. So what we do is make the effort to try and explain so that society can be informed about these consequences. And I think this is a way in which some societies no longer are giving sufficient value to appreciating the significance of scientific knowledge and scientific information and its consequences for society. I don't want to be too specific, but we can all think of the US climate change debate as an example where not enough effort was made to provide the information to a broad enough base of the voting public that they simply don't understand the consequences of the vote. And so the implications of what you say are very important, not just in sciences, but for all of society.
Any other questions, comments?
There's one out in the middle down the back.
There's one at the back.
We've got a frontist bias.
Yeah. Jerry mentioned the distribution of the magnitudes of stars. I just wondered whether we've got any handle on the distribution of the black holes and their masses.
Oh yes, yeah, we know a great deal. Astronomers are very good at weighing things. That's what we do, really. We weigh stuff. And so we've developed over the last couple of decades a classical Newtonian method of weighing things. You know, we weigh the sun by essentially timing how long it takes the Earth to go around the sun. As it happens, we call that a year. And that tells us how heavy the sun is. We can do the same thing by watching the speeds of stars near supermassive black holes. And it turns out that essentially every galaxy, like our Milky Way or bigger, in fact even probably much smaller ones, has a black hole in its centre, and the mass of that black hole is intimately related to the total number of stars in that galaxy. And now that's really weird, because the black hole is smaller than a solar system and the galaxy is truly huge, but nonetheless this is what nature does. So there are as many giant black holes in the universe as there are galaxies in the universe. Sorry, some of your microphones.
Sorry, I didn't notice.
Not working.
You're fighting against a helicopter.
What is the percentage of the mass of a galaxy typically that's in black holes?
Oh, the fraction of the mass that's in the black hole is absolutely tiny. It's quite insignificant. The black hole is important locally, but only very, very locally. So it might make up the fraction is 10 minus 4, so 1/100th of 1% of the mass of the galaxy is in the black hole. So as soon as you get more than a light year away from it, you wouldn't know it was there.
And what percentage of stars are black holes?
Again, it's a small fraction. It's about 1/100th of 1%. So the only stars that become black holes are massive stars, and massive stars are intrinsically rare. But some of them are nearby. You know, we can see them merging now through gravity waves and so on. So there's lots of them up there by number, but that's only because there's such a ridiculously prodigious number of stars up there. But as a fraction of the total mass, it's tiny, but as a fraction of the total fun function, it's huge.
I think we should.
About that, yeah.
I think we have a question in the middle.
There was one
there.
out in the middle somewhere. Oh, here we are.
So, would you consider Fleming's discovery of penicillin as a blunder that became a breakthrough, in this case, for antibiotics? And do you think we actually have much opportunity to make blunders that become great discoveries nowadays?
I didn't quite catch that. Could you say that again louder, please?
Yeah.
Sorry. So, would you consider Fleming's accidental discovery of penicillin a blunder that became a breakthrough, in this case for antibiotics? And do you think we actually have much opportunity to make such blunders nowadays?
Ooh, discovery of penicillin as a blunder. Would anyone like to take that on?
Well, it was to some degree. Sorry, please. You're the expert.
Well, actually, there are lots of such examples, actually. There are a lot of examples like that, particularly in the first half of the 20th century, where where experiment was far ahead of theory. And an amazing number of things were discovered because somebody left an experiment running overnight, or the fridge broke down and the temperature changed, or something like that, or somebody left an unexposed photographic film near an X-ray source without knowing about it. So there are a very, very large number of things that were, after the event, highlighted as triumphal successes, but at the time was somebody making a blunder or a screw-up. Yeah. These days we learned, and so now when our students do things like that, we first check the answer before they tell them they were stupid.
And penicillin is a particularly interesting one. That actually there are a number of accounts of people noticing or finding penicillin before Alexander Fleming noticed it, but they never reported it. And indeed, in a number of peasant cultures, there is a treatment actually strapping mouldy bread onto a wound. Completely empirical, nobody knew why, but it was an old wives' story that there would be some good came out of that. So penicillin is an interesting issue. But you suggested, the second part of your question was, would there be another breakthrough like that? Which Jerry sort of hinted that, yes, there may be. Helen, John?
Back to the same point really, which is about experimentation, and you don't always know what you're going to get out. So you make some predictions and a hypothesis, and you may or may not meet that, but other unexpected results may come. And that's, I guess, the whole point of science, is that, as we know, you don't always know the outcomes, and you're doing a series of experiments to test a series of hypotheses, and it's all going to depend on the data and the methods that you use to do those experiments.
Accident favours the prepared mind, they say. I think all these cases, they must have been very, very close to getting it without the accident. Otherwise, that would just be dirty washing up that they needed to do with the saucerful or whatever. I think these are a bit romantic tales. When you look more carefully, the element due to accident is a lot less, and the element due to almost being there theoretically a lot more.
Question in the middle there, yes.
Good day. My question relates quite a bit to the previous question, in that I'm actually a scientist, and some of the most my biggest successes have been because I've what I refer to as boo-boos, although sometimes we use harsher words. And my previous boss would refer to them as serendipitous discoveries, which is how we wrote it in the last paper. But because of these boo-boos, I've been we found things out, and they've become quite fond things eventually. But I think it's got a lot to do with the vocabulary that as scientists we're taught to not think of blunders as blunders. We just take the blunder, we learn from it, and it becomes a boo-boo, or a serendipitous, result. With that in mind, I'd like to hear if any of you have any boo-boos that you're particularly fond of or that you'd like to share, just as a fellow scientist. I think the rest of the room would probably also like to hear about something like that.
Anybody want to admit or boast?
I spent a lot of time making evolutionary trees of gibbons, many of which were wrong. And in fact, we still don't know what the true relatedness amongst different species of gibbons are. And now we've decided just to give up. That's a massive boo-boo.
A slightly more positive example. Early in my career, I was trying to find quasars, high black holes at very large distances. And quasars look just like stars, so I thought I'd better get rid of all the stars. So I made a little model of the Milky Way, see how many stars there should be, so statistically I could get rid of them. And I didn't know anything about the subject of stars in the Milky Way, so I just worked out a model that fitted what the observations on the sky did, so I did the inverse of what Newton did. And then after the event discovered that this model was completely contradictory to the standard model in the literature, and that the standard model was wrong. Now, had I been better educated, I would have done it the other way around and never made what has actually turned out to be a very substantial discovery. So yeah, like yourself, congratulations to you, and I've boo-booed as well.
We have time for a couple more quick questions. A gentleman in the green and white shirt, and then the gentleman in the front here.
Thank you. I don't have a scientific background, so I'm just an enthusiast. Will there be a time when we will be able to use quantum entanglement as a means of communication? So if yes, how long do you think we are from that?
Okay, that's probably me, I
Yeah,
should think.
Jerry?
Yeah. The answer is yes, there will be a time when we can use quantum entanglement, and the time is probably about a decade away. Experiments that work exist now over distances that are quite long, hundreds of kilometers. And so the technology exists to do a minimal information transfer already, and it's reliable. And so it's proven technology. It's just a question of engineering from here on in.
And there's a gentleman here at the front, white shirt.
Hello, can you hear me okay? Okay. I can't hear myself. When I took physics in high school, I remember, of the many things I remembered of physics, is that the teacher described it that science and physics and chemistry, these are, science is the search for the truth. So how do you search? And then the answer came back, well, you come up with theories and then you test those theories. and as your tests succeed, your theory is proven better. But the point is, you're still trying to get the truth. And so I'm sort of convinced, John, of what you were saying, that before I came here, I didn't think I was going to, I thought I was going to, hear entertaining stories. But I actually think you're right that there are no blunders. All there are failed tests. And then you use the definition of blunder as stupid. Okay, there had to be a stupidity involved. Well, and then I think, Jerry, you use the example of one stupid thing that Newton may have done. But, I mean, Newton being stupid is different from me being stupid because I'm not a scientist. And so I like the idea that failed tests are not blunders. They are actually successes. Now, I come from a computer background. And so I remember one of the things I learned with testing computers is you got to reduce the defects. You got to have the less number of bugs. And so each time you were counting the number of bugs in your program, the higher it was, you were deemed a poorer programmer. Well, I like it the flip side, where the more number of failures and the more times you prove your program wrong, the better, because that's one less chance that the program's going to get out in the wild and have that problem. So I like the idea that there really are no blunders. There are just failed tests. And who is stupid? Well, it has to be, you have to have credentials and prove yourself to be either less stupid or more stupid.
I think that's a very useful point to finish on, as we are almost out of time, and it is a hot Sunday afternoon. I would, however, just like to ask the panelists one final question, and that is, what in 100 years' time, when our grandchildren are sitting here, what do you predict they might call the blunders and breakthroughs of today? Helen, do you want to lead on that?
I guess for me it's going to be climate change. There's still a lot of the population who don't believe in climate change. I'm pretty sure in 100 years' time, most people will believe in it. I hope.
Well, it's always tempting to say, well, science has done amazingly well and just the next step and we'll have a theory of everything. In my subject, I find it quite humbling to know that we have actually only a partial knowledge. We have a knowledge of the basic properties of 4.5% of the universe. All the rest of it's made of dark matter and dark energy. We haven't got the slightest idea of what dark matter and dark matter energy is. I weigh the stuff, so I know it's there. So I think in 100 years' time, I hope that people will look back and say, boy, they were really ignorant, but we're much better educated. We've learned all these things.
Yeah, I certainly don't think we'll have a theory of everything. That was a real boo-boo by Hawking. Newtonian physics, classical physics used to think the same. Physicists would curse Newton for having discovered the truth about the universe. It was just a matter of dotting a few I's and crossing a few T's, and there's nothing left for them to do. So I certainly think there may be revolutions in the same sense that we had an Einsteinian revolution or the classical scientific revolution originally, which replaced the theories that we have now. But like I said earlier, I do think, at least in the solid areas of science, and then there'll be lots of other things we've learnt as well, but in the solid areas of science, like quantum mechanics, like general theory of relativity, those revolutions, quote unquote, will lead us to theories that tell us that they were what you had before was not quite right, but it was pretty good. I think we should be more positive about what we've got in science and not worry so much about the possibility that it may be overthrown. Very likely overthrown in this sense that Newton's theory has been overthrown, namely overthrown but kept on in a very important way.
Thank you very much. As I say, it's a hot Sunday afternoon. You've been a wonderful audience, very attentive, and some wonderful questions. Thank you all very much for coming. And I'd like to thank our three experts, Jerry, Helen, and John in particular, for spending this time with us. And they will all be around for a little longer if you want to come and see them to ask further questions. But may I ask you to join me in thanking them for their time.
Thank you very much.